Chapter 11 Reactions of alkyl halides, Nucleophilic substitutions and eliminations. Because carbon and halogen atoms have different electronegativity, alkyl halides are polarized at the carbon halide bond, making the carbon atom partially positive charged. When a negative charged group such as hydroxy comes closer to the molecule, it will attack the positive charged carbon and replace the halogen atom, forms an alcohol. So the net effect is bromine is replaced by hydroxy, and the reaction is nucleophilic substitution reaction. Now, hydroxy may also serve as a base that reacts with a proton. So here, hydroxy reacts with the proton adjacent to the carbon-halogen bond. And when the proton is deprotonated, carbon-bromine bond break, it forms a alkene. So the net effect is the reactant lose hydrogen bromide. And the reaction is called elimination reaction. In this chapter, we are going to look at the mechanisms of these two types of reactions and discuss the factors affect these reactions. Nucleophilic substitution, base-induced elimination are among the most common reaction types in organic chemistry. So in this chapter, we are going to look at how they occur, what are their characteristics, and how they can be used. Nucleophilic substitution reactions undergo two types of mechanisms, SN1, SN2. If we have a mixture of hydroxy and 2-bromobutane with a S configuration, you may confirm this chiral molecule has a S configuration. Hydroxy is called a nucleophile. Phile means love. Hydroxy has lone pair electrons that is attracted by positive charged nucleus. Now, the negative charge makes hydroxy a strong nucleophile. So what happens is hydroxy will attack positive charged carbon and push the carbon-bromine bond break. So the bromide leaves the molecule, forms a new carbon-hydroxy bond, carbon-hydrogen or oxygen bond. And note that the configuration changes from S to R. So in the reactants, the substituent bromine is on the right side. In the product, the hydroxy is on the left side. And this is a complete inversion of the chirality center. And also the reaction rate depends not only on the alkyl halide A, but also on hydroxide. So if you increase either of them, the reaction rate will increase. The reaction follows a second-order reaction, and therefore this reaction is called nucleophilic substitution SN2. 2 means it's a second order. Both alkyl halide and the nucleophile are important in the reaction. Now, SN2 reaction usually happens when you have a strong nucleophile, such as negative charged hydroxy, with a less crowded alkyl halide. And in this case, this carbon is a secondary. It is even better if we have a primary alkyl halide. Now, if we use a crowded alkyl halide, such as this one, which is 6-chloro-2,6-dimethyl-octane, the carbon here is a tertiary, very crowded, and with a nucleophile water. Water is a neutral molecule. It has lone pair electrons, so it's attracted to the nucleus. So it's a nucleophile, but it's a weak nucleophile. It's a lack of negative charge. So if we combine these two together, the product is also hydroxy alcohol, but one is a mixture of S configuration and R configuration in almost the same equal amount. Okay, it's a racemic mixture. All right, and the reaction rate depends only on this alkyl halide, A, not water molecules. So the reaction rate law is first order, only depends on A, and the reaction is called SN1. The important feature for SN1 is you make a racemic mixture instead of the complete inversion of a reacting center for SN1 or SN2 reaction. Okay, SN1 reaction usually happens when you have a weak nucleophile such as water and a crowded alkyl halides such as tertiary or sometimes secondary alkyl halide. Let's look at SN2 mechanism in detail. Hydroxy is a nucleophile, so it will attack positive charged carbon. We draw an arrow to show how electron flow. The tail of the arrow should go from the two electrons, okay, of a lone pair electron, and the head should go to the carbon, and that indicates the two electrons of a lone pair electron go towards the carbon to form a new bond, oxygen-carbon bond. Now, carbon can only form 4 bonds. So if a new bond forms, then old bond has to break. So we draw another arrow. And this arrow shows the 2 electrons that originally forms carbon-bromine bond will break and go completely to bromine to form a bromide. Now remember, this is a process. So if a new bond forms, the distance between oxygen and carbon has to become closer and closer. And if a carbon-bromine bond break, the bond distance must increase. There is an instant where these distances are comparable, and this is called a transition state. So in a transition state, the oxygen-carbon distance are close enough, okay, almost form a new bond, and the carbon-bromine distance becomes longer and almost break this old bond. And this transition state is a high energy instant state. Okay, it's not a compound. All right, you cannot isolate it. It's an instant between a reactant and forms the product. All right, and then the old bond break and new bond form, and that's the product. Okay, so again, you can see that hydroxy attack carbon forms a new bond, and the old bond break, bromide leave. Okay, so here are some important features for SN2 reaction. First, nucleophile attack carbon cation from back of the halide, because hydroxy attack carbon, not bromine. So if hydroxy go from this side, on the right side, bromine will block carbon. It cannot attack carbon, so it has to attack on the back. All right. Second, the reaction involves a transition state. Transition state is the state, an instant where new bond has not established yet, but almost, and old bond is not broken yet, but almost broke. All right, it's an instant, but it's not a compound. It's not a stable compound. You cannot isolate it, and therefore the reaction only have one single step. Okay, so single step, not the 2 steps. It's not a intermediate. Intermediate is a stable compound, even though it's not very stable, but you sometimes can isolate. So it has a significant time to exist, and therefore you forms intermediate. That's one step, and the intermediate forms another. That will be a different step. But here, the transition state is not intermediate. It's just the instant where the old bond is almost break, the new bond is almost formed. All right. So the reaction, the whole reaction is just one step, not 2 steps. Okay. Finally, the inversion of stereochemistry. So from S configuration becomes R configuration. In SN2 reaction, the kinetic center inversion can be compared to an umbrella inversion in wind. When strong wind blows towards the umbrella the umbrella can be inverted. Similarly, when hydroxy attack a carbon cation on the back of the bromide, the product will have inverted chirality center. This shows the structure of transition state. So this is a nucleophile. It could be hydroxy. All right, and this is alkyl halide. So this can be chlorine, and this is carbon, and with 3 hydrogens. So the nucleophile approach the carbon cation, and so becomes closer and closer, and the old bond becomes longer and longer, and at a certain instant, so the bond, okay, this new bond is almost formed, and old bond is almost break, and that's transition state. And then old bond break forms a chloride ion. That's the chloride ion, and this is the new product, alcohol product. Okay. Also notice that both the reactants and the product, the carbon is sp3 hybridization, tetrahedron geometry. So angles are all 109 degrees. But in transition state, the carbon is roughly a planar arrangement. Here shows the energy profile of SN2 reaction. This is the energy of the reactants, and this is the energy of the product. The fact that the energy of the product is lower indicates the product is more stable. So thermodynamically, the reaction is favorable. Before the reactants go to the product, it must go through a high energy transition state. Here, the carbon is connected to almost 5 atoms because the old bond is not broken yet, and the old new bond is almost formed but not formed yet. So this is a high energy transition state. The energy barrier here is called activation energy. This energy determines the reaction rate. Exercise. What product would you expect from a nucleophilic substitution reaction of 1 bromo 1 phenylethyl, okay, with an R configuration, with a cyanide? So this is a cyanide as a nucleophile. Now note that sometimes we omit lone pair electron, but it's there. Okay, we just don't join it. So it's this lone pair electron that will attack the carbon. Also note that for line bond structure, we omit carbon hydrogen, but remember they are there. So for example, in this molecule, there's a carbon here, and there's also a carbon here. All right, and remember each carbon forms 4 bonds. So the end carbon should have 3 hydrogens. So this carbon should have 3 hydrogen, and this carbon should have 1 hydrogen, so that it has 4 bonds. Okay, now how do we draw R structure, okay, configuration? Now in organic 1, you learned that first we rank the substituents around the chirality carbon. So this is the chirality center, all right, and we rank according to the atomic number. Bromine is the highest ranking, so it's number 1. And then these 2 are both carbon, but this carbon connect to another 2 carbon and also double bond. So this carbon has a higher priority than this, the right side. And then hydrogen is the lowest ranking, so it's number 4. Okay, so that's the first step. You rank all these atoms, and then you orient so that number 4, the lowest ranking one, should pointing away from your eye. So imagine here is your eye looking at the molecule. You should let number 4 away from you. All right, and then you look at the rest. Number 1, start from number 1, and then number 2, and number 3. If this order is clockwise, then it's R configuration. On the other hand, if 1, 2, 3 is a counterclockwise, that's a RS configuration. When you do that, you will find that the molecule should have this structure. The hydrogen should be in front of the paper, and the bromine should be on the back. And this will give you a R configuration. Okay, let's confirm it. Suppose your I is on the back of the paper, and you're looking at this carbon. And this way, the hydrogen is pointing away from you. Okay, because hydrogen in front of the paper. So in order for the hydrogen to be away from you, you put your eye on the back of the paper. All right, and then you look at other atoms. So this is number 1. All right, and so let's arrange here. Number 1, okay, is on the top, and then from back of your eye, this number 2 carbon should on the right side. Okay, imagine your eye on the back of the paper. All right, so number 2 carbons should be on the right side of your eye. So here number 2 is on the right side. So this is the carbon. All right, number 1, number 2 is on the right side, and this one, number 3, should be on the left side of your eye. So this is left side, number 3, and then you orient 1, 2, 3, and that is a clockwise. So that's why it's called R configuration. So we confirmed that this is an R configuration where hydrogen is in front, bromine is on the back. All right. Now nucleophilic substitution reaction. This will attack here, and the bromine will leave. So the net effect is bromine will be replaced by cyanide. So you should draw a structure: bromine replaced by cyanide. Also remember the complete inversion of chirality center. So if hydrogen is in front of the paper in the reactants, then in the product, the hydrogen should be on the back. And bromine is on the back of the paper in the reactants, then the new substituent should be in front of it. Okay, so R configuration now becomes S configuration. So far, we discussed the SN2 reaction mechanism where a nucleophile, such as hydroxy, will attack the carbon on the back of the halide, leading to a complete inversion of chirality center. What if the alkyl halide is crowded? All right, so the carbon is shielded by these large groups, which makes it difficult for the attack from the nucleophile. So in this case, the reaction may undergo a different mechanism, and that is SN1 reaction. In SN1 reaction, okay, the first step is the carbon-halogen bond break. So the 2 electrons between the carbon-halogen will go completely to bromine to form a bromide. And because the carbon loses electron, it forms a cation called carbon cation. And in carbon cation, the carbon only connect to 3 bonds, 3 atoms. All right. So note that in the reactants, the carbon has 4 bonds. It's a tetrahedron geometry. But in the carbon cation, because it forms 3 bonds, so it's a planar structure. Okay, so these are in the same plane, and you have an empty p orbital. Okay, because it's a carbon cation, so the p orbital is empty, and because the carbon cation it lacks of electron, so it attracts lone pair electrons, electrons. So if you have a hydroxy, now the second step is the hydroxy will donate electron to this empty p orbital. There are 2 ways to donate. One is on the top of it or on the bottom of it. When the oxygen donates the electron on the top, it forms a bond, carbon-oxygen bond, leads to a S configuration alcohol. Now, when the oxygen donates the electron on the bottom to form a carbon-oxygen bond, it forms a R configuration. So in theory, it will give you 50-50% of S and R configuration mixture. That's called a racemic mixture. All right. So we have seen that for SN2 reaction, the nucleophile attack directly to lead to complete inversion of catalytic center. But in a SN1 reaction, first step is carbon-bromine or halogen bond break, and then attack, two ways attack to give a racemic mixture. Here shows the energy profile for SN1 reaction. Now let's compare with SN2 reaction. In SN2 reaction, the energy profile has a energy of reactants, energy of product, and there's a transition state. So go through a transition state, all right? And the energy barrier E determines reaction rate. Now, if you look at the SN1 reaction, the energy profile has a energy minimum here, and this represents the carbon cation intermediate. So carbon cation intermediate, even though it's not very stable, but it can exist in a significant amount of time. All right, so it has an energy minimum. So you have two transition states. This is the transition state that leads to the carbon cation. So that's is a first step reaction. So carbon halogen bond break through a transition state forms carbon cation. All right, and this is the energy barrier that determines reaction rate for the first step. And then for the second step is the carbon cation react with nucleophile through another transition state, forms the product. And so first notice that for SN2 reaction, it's only one step, transition state to the product. But for SN1 reaction, you have two steps, two transition state, all right? But the first transition state has a higher energy, so you need a high energy barrier than the second transition state, okay? And therefore, the first step is slow, and the second step is fast. The slow step determines the total reaction rate. So the whole reaction is determined by the first step, called the rate limiting step. The rate limiting step is to form carbon cation. All right. So if carbon cation is stable, for example, the energy is here, then you need a small transition. The energy transition state is small, and then that will increase the reaction rate. So the more stable the carbon cation, the faster the SN1 reaction will go. Having looked at the reaction mechanisms of SN1, SN2, now let's look at the factors affect these reactions. Nucleophilic substitution reaction involves a nucleophile and a alkyl halide we call substrate. For SN2 reaction, it's the nucleophile directly attack the substrate. So the stronger the nucleophile, the faster SN2 reaction goes. Strong nucleophile usually are negative charged nucleophiles. Now, because the nucleophile attack the carbon on the back of the halide, and so the steric effect is important. The small substrate favors attack, so it favors SN2 reaction. Okay, so methyl alkyl halide is the fastest, and then secondary, the tertiary is too slow for the SN2 reaction. Now later we'll show you tertiary alkyl halide actually forms a stable carbon cation which favors SN1 reaction. Okay, so large substrate favors SN1 reaction, small substrate favors SN2 reaction. Now leaving group is important for both SN1, SN2 reaction because the reaction will replace the leaving group. All right, so the better the leaving group, the faster for both SN1, SN2 reaction. And solvent is also important. Polar solvent, aprotic solvent favors SN2 reaction. Protic solvents favors SN1. So we're going to explain what is protic and aprotic solvents. We already mentioned that negative charged nucleophiles are stronger, and so they are usually more reactive. And the conjugate base is always a stronger nucleophile. For example, hydroxy is much stronger nucleophile than water. Amide, which has a negative charge, is much stronger than amine. And hydrogen sulfide ion is much stronger nucleophile than H2S. Now, SN2 reactions are often carried out under basic condition because these stronger nucleophiles can only exist in basic condition, and SN2 reaction requires stronger nucleophile. A nucleophile refers to an atom or a group that loves the nucleus. For example, hydroxy, we already seen this, negative charged hydroxy will attack positive charged carbon, and this makes hydroxy a nucleophile because it loves the nucleus. Now, what is a base? A base is an atom or a group loves proton. For example, again, hydroxy. It can attack proton to form water. So hydroxy is a strong base. Now, usually a strong base that can attack proton can also attack nucleus, carbon cation, because they are electron rich, and therefore nuclear facility roughly parallels basicity. Strong base usually also a strong nucleophile. Now let's look at methane, carbon with 4 hydrogens. Okay, if this methane loses a proton, it forms carbanion, and carbanion is extremely unstable, okay, very reactive, because it wants this proton back, and so it's a very strong base. All right, strong base is also a very strong nucleophile. Now let's look at amine. Okay, amine has 3 hydrogens. Okay, we already know from Jenkins, amine is a base. All right, it's a base in likes to a proton. But if we lose a proton, it becomes even stronger base. That's amide. Okay, NH2 negative. That's a very strong base. But this base is weaker than carbanion. The reason is nitrogen has a larger electronegativity than carbon, so it holds this lone pair electron better than the carbanion. All right, carbanion when lose a hydrogen, all right, it has a lone pair electron. That make it very unstable. Amine, when it loses electron, it has 2 lone pair electrons. Okay, a negative charge. But the nitrogen is more electronegative, and therefore it holds these lone pair electrons better, and so it's slightly more stable and less reactive. So it's a weaker base compared to carbanion. Okay, so weaker base. Okay, if water loses a proton, it forms hydroxy, and so we know hydroxy is a strong base, but it's weaker than amide, and also of course weaker than carbanion, because oxygen has a much higher electronegativity, so it holds those lone pair electrons much better and make it more stable, so not as reactive. Similarly, fluoride is the weakest base among these bases. So across the period, all right, the basicity decrease, all right, go to the left side, the basicity increase, and the nucleophilicity also increase. Carbanion is a very strong base, also very strong nucleophile. Now we learned some examples of carbanion. Okay, what are they? Well, one is Grignard reagent. So remember, Grignard reagent, magnesium bromide. Okay, this carbon is a negative charge, so it's a carbanion. So Grignard reagent is a very strong base. It attacks water. It's very water sensitive. It's also a very strong nucleophile. When go down a group in a periodic table, the atoms becomes, or ions becomes larger and larger. So fluorine is small, chlorine is larger, iodine is largest. All right. When the size becomes larger, the electron clouds are far away from the nucleus, and it becomes more polarizable. Okay, and that make them more reactive. Okay, for example, if you have a charged carbon cation, and when iodide moves towards carbon, because iodide is so big, the electrons cloud are so loosely around the iodine, it easily go towards the carbon. All right, we call it polarizable, and so it is more reactive compared to fluorine. The electron tightly bonded to the fluorine, so it's less reactive. Here is a comparison of different nucleophiles and their reactivity. In general, charged ions are better nucleophiles than neutral molecules. In particular, those large negative charged ions, for example, sulfide, phosphorus, Grignard reagent, iodide, these are extremely high, large, good nucleophiles. And those good bases, very good base, hydroxide, methoxide, and N3 negative, bromide, they are good nucleophiles, and they favor SN2 reaction. On the other hand, neutral molecules, here is water. Okay, here is methanol or ethanol, alcohols, and carboxylic acid, and conjugate base from strong acid. They are weak base, and therefore weak, very weak nucleophiles, and they prefer SN1 reaction. In between is this fluoride, chloride, neutral amine. Okay, these are fair nucleophiles. We already mentioned the steric effect for the substrate. So for a methyl bromide, carbon is connected to 3 hydrogens. So these are the hydrogens. The carbon is exposed, easy to be attacked by SN2 reaction. So it's the best for SN2 reaction. In ethyl bromide, okay, 1 hydrogen is replaced by bromine. So now part of the carbon is shielded. But it's still a large amount of carbon is exposed for the attack. So this is still good. It's a primary carbon, so it's good for SN2 reaction. Now, if all the hydrogen is replaced by methyl, okay, in tertiary carbon, then you can see the carbon is completely shielded by the hydrogen, and it's the worst for SN2 reaction. Okay, later we'll show this is actually good for SN1 reaction. This is experimentally determined relative reactivity of different substrate on SN2 reaction. So for a methyl bromide, the relative reactivity is 2 million. And if you change to ethyl bromide, the reactivity reduced to 40,000. So here is a secondary now, and the reactivity becomes 500. Note that this is still primary carbon, okay, only connect to 1 carbon, but this carbon is so crowded that SN2 reaction is very unfavorable, so the reactivity becomes only 1. All right, tertiary, the least reactive, actually is so insignificant that almost no reaction for tertiary in SN2 reaction. We already mentioned that tertiary alkyl halide is worst for SN2 reaction, but good for SN1. Why is that? Well, this is the energy profile for SN1 reaction. It has 2 steps. Okay, here is the carbon cation, and this is the first transition state, and this is the second transition state. Because the first transition state has high activation energy, so this is a slow step, rate determining step. So the whole reaction determined by this transition state, the activation energy. Now, if the carbon cation is more stable, then the energy is lower. So this is the red curve indicates you form a more stable carbon cation because energy is lower, and then the transition state is also lower. This leads to a smaller energy barrier and leads to a faster reaction. So the stable, the more stable the carbon cation, the smaller the activation energy, the faster the reaction goes. It turns out that carbon cation for tertiary is the most stable carbon cation, and then secondary carbon cation, and then primary and metal is the worst. All right, so tertiary carbon cation is the best. So if tertiary alkyl halides, for example bromine, it will easily break the bond, forms carbon cation because it's more stable, and because more stable, so the reaction go faster for SN1 reaction. In a nucleophilic substitution reaction such as this one, bromide is replaced by hydroxide, so bromide is called a leaving group. A good leaving group is important for both SN1 and SN2 reaction. But what kind of leaving group is good? A good leaving group is when the product, the ion after it leaves from the alkyl halide, is stable. Because the more stable the product, the easier for the reactant to go to the product. So the more stable the ion, the better the leaving group. Here is a chart I want you to remember, at least the trend, all right, about the leaving group. Okay, these are strong base, hydroxyamide. Okay, as we shown before, they are negative charged ions. They are very reactive, attack hydrogen and carbon cation, so very reactive. Very reactive means they are not stable, and not stable they are bad leaving group. So these are very bad leaving group, including fluoride, and therefore alkyl fluoride, alcohols, ethers, amines, they do not typically undergo SN2 reaction, because let's say if this is methanol alcohol, all right. So if under SN2 reaction, then this will forms hydroxide, but the hydroxide is very unstable, so the reaction very difficult to form. All right, so they typically do not undergo SN2 reaction. Okay, now alkyl halides, so the chloride is a much better leaving group than fluoride, and the bromide is a very good leaving group. Iodide is very good, okay, much better than iodide. Okay, so the heavier or larger the size of the anion, the more stable and the better the leaving group. Now, even though hydroxide is a bad leaving group, but in acidic condition, we are going to see in the future, if you have acid, this can protonate this one, forms OH2+. Okay, so now if this leave, it forms water, and water is a good leaving group. The reactivity of water as a leaving group is about between bromide and iodide, so that's a very good leaving group. All right, so you see a bad leaving group sometimes can be converted into a good leaving group. A good leaving group is particularly important for SN1. It's important also for SN2, but more important for SN1, because SN1, the first step is the carbon halide bond break, forms leaving group leave. That's the first step. All right, so it's more important. In the last slide, we show a chart of leaving groups, some good leaving groups, some bad leaving groups. Among them, one of the best is tosylate. Okay, sometimes we write as TOSO-. And here is the structure with a toluene sulfonic called tosylate. So last slide, we also show that a good leaving group is when the corresponding ion is very stable. So what makes this ion stable? Okay, now in organic 1, you learn the drawing resonance structure. So if you draw resonance structure, you can see this can draw many resonance structures. So one of them is like this. Okay, so the negative charge on the left side of oxygen now becomes negative charge on the top oxygen. You can draw another resonance structure, put negative charge on the bottom oxygen. You can also draw resonance to move electrons on the benzene ring. And so the resonance structures stabilize this anion and becomes an excellent leaving group. In the last slide, we showed hydroxy is a poor leaving group, but it can be converted into a good leaving group by adding proton, forms a water, very good leaving group. Alternatively, it can be also converted to tosylate, so hydroxy becomes tosylate. That's an excellent leaving group. A bad leaving group, hydroxy, can be converted into a good leaving group by adding acid. So protonate forms oxygen ion, and when this leaves, it forms water. And water is very stable, so that's a good leaving group. And that forms a carbon cation. And then chloride attack carbon cation forms alkyl halide. So the net result is hydroxy replaced by chlorine. And this reaction is SN1 reaction. Why? Because it has two steps. It forms carbon cation and then chloride attack. So two steps, carbon cation involved. That's a SN1 reaction. Now in chapter 10, we learned alcohols, okay, particularly primary and secondary, can be converted into alkyl halides by adding dinyl chloride or phosphorus tribromide. And now we can show the mechanism, and they actually first forms a good leaving group, and then chloride attack, and these are SN2 reactions. So in the next two slides, we're going to see the detailed mechanisms. It is very important that you can draw the mechanisms of these reactions. Let's try to draw an SN1 reaction mechanism. Okay, if you are not familiar with drawing mechanism, you must practice. Okay, grab a pen and a paper. Let's draw together. Try as many times as possible until you are confident you can draw the mechanism, because it's important to learn organic chemistry, all right, to draw mechanisms. So let's convert a tertiary alcohol. So here is a tertiary alcohol into a alkyl halide. Okay, remember, tertiary alcohol SN2 does not happen, because for SN2 reaction, the first step is nucleophile attack carbon on the back of the leaving group, which cannot happen because tertiary is crowded. Okay, instead it undergo SN1 reaction. But for SN1 reaction, the first step is the leaving group leave. But hydroxy is a poor leaving group. All right. So in order for the leaving group leave, we first must convert hydroxy into a good leaving group, and that's why alcohol for SN1 reaction usually take place in acidic condition to change to a good leaving group. So let's draw the mechanism. So first draw this alcohol. Okay, particularly draw the lone pair electrons, okay, of oxygen. All right, and then draw hydrogen chloride. Okay, that's the acid that will protonate hydroxide. Draw an arrow so that to show the lone pair electron of oxygen flow to the hydrogen to form a bond between oxygen and hydrogen. So it's form a bond to protonate this hydroxy. At the same time, draw another arrow to show hydrogen chloride bond break, and the two electrons between hydrogen chlorine goes to the chlorine to form a chloride ion. So the product here is an intermediate, right? It's OH2 plus, because now one hydrogen becomes two hydrogen, the oxygen becomes positive charge. Okay, so now the hydroxy is converted into a good leaving group. This is when SN1 mechanism starts, because SN1 reaction is leaving group leave. So draw an arrow, show the two electrons between carbon and oxygen move to oxygen, completely give to oxygen, forms water. And at the same time, the carbon lose electron, forms a carbon cation. So that's a rate determining step. First step forms carbon cation. All right, and then so of course you have water. All right, and then a nucleophile, which is chloride. that generated from the first step comes in, okay, draw the chloride, draw the lone pair electrons, all right, and the negative charge. So the next step is the lone pair electron attack the carbon cation, okay. Now many students make a mistake, not sure how to draw arrows. The arrow tail shows where electron flown. It flown the lone pair electron, and the head show where electron go. It goes to the carbon cation, and that forms a bond between carbon chlorine, and this gives you the final product. So the SN1 reaction actually starts from this oxygen ion, all right, 2 steps, okay. SN1 reaction always involves 2 steps. First step forms carbon cation, second step nucleophile attack forms the product. But for alcohol, you need an additional step, that's the protonation step to make a good leaving group. Okay, so protonation form a better leaving group, all right? And that's the mechanism, complete mechanism to convert a tertiary alcohol into an alkyl halide. In the last slide, we showed the mechanism of SN1 reaction. A tertiary alcohol is converted to a alkyl halide. What about the primary and or secondary? Okay, primary, secondary alcohol, you need a thionyl chloride or phosphorus tribromide. First step, you still make a good leaving group, but now you don't need acid, just the reagent itself. So what happens is the thionyl chloride, that's the structure. Now the bond here, negative, positive, so it's a polarized bond. So alcohol has lone pair electron, will attack the sulfur, okay? And then one of the chlorine leave form a chloride, and that gives you a good leaving group. Now this oxygen bonds to sulfur, okay? Oxygen, sulfur bond, so that's a good leaving group, okay? At the same time, you form a chloride. Now, if you are not familiar with these steps, okay, you don't have to draw these steps. You can simply show that the hydrogen is removed with another chlorine, so SOCl2. So one of the chlorine come out with the hydrogen. At the same time, the oxygen combined with SOCl. So this is OSOCl, and that is a good leaving group. Similarly, the proton with a bromide, so bromide come out, so oxygen combined with phosphorus with 2 bromine, all right? That's a good leaving group, okay? So the first step, you change hydroxy into a good leaving group. In either case, you change into a good leaving group. At the same time, you generate bromide or chloride. Okay, that's when SN2 starts, okay? Because SN2, these are primary or secondary, so SN2 favors SN2. So bromide attack on the back of the leaving group, and the leaving group leave. Okay, so the product is chloride or bromide, all right? So notice that the characteristic change for reactants, hydroxy is on the right side, the product chloride on the left side, and the bromide on the left side. All right, so that's a example of SN2 reaction where a primary secondary alcohol is converted to a alkyl halide by SN2 reaction. When an ionic compound is dissolved in water, for example sodium chloride, the chloride can be solvated by water molecules. Because water has a polarized bond, oxygen is negative charged, hydrogen is positive charged. The positive charged proton will be attracted to the negative charged chlorine. So one chlorine can attract many water molecules. So each molecule pointing its proton towards chlorine. And this will stabilize the negative charged chlorine. Now remember, negative charge make chloride a fairly good nucleophile. But because this solvation effect, chloride is solvated by the water molecules, it becomes less reactive. Okay, so it's less reactive in SN1, SN2 reactions. Water is not the only solvent that can stabilize negative charged ions. For example, methanol. So methanol also have polarized bond. Oxygen is negative, hydrogen is positive. So the positive proton can stabilize negative charged ions. But not all hydrogen can stabilize negative charged ion. For example, in methanol, okay, so you have 4 hydrogen, but the bond is not polar. The hydrogen is not a positive charge, so it cannot stabilize anions. Only those compounds that involves OH bond, NH bond, SH bond, because oxygen, nitrogen, sulfur, they are negative charge. They are electron negative, and therefore they make protons, hydrogens positive, and the proton positive proton like a proton. All right, hydrogen like proton. So therefore, these solvents are called protic solvent. Okay, some examples include methanol, ethanol, water, amine. So amine, you have NH bond, so hydrogen is positive, and carboxylic acid, you also have hydroxy. So the hydrogen is a positive charge that can stabilize anion. So in this example, so water, you have proton pointing towards negative charged fluorine, stabilized fluorine. And when fluoride is stabilized, it will not react, all right? So that will slow down SN2 reaction, because SN2 reaction requires nucleophile to attack the carbon cation, the alkyl halides substrate, okay? So if this is stabilized, then it will slow down the SN2 reaction. In the last slide, we showed the protic solvent, where the molecules contains OH bond, NH bond, SH bond. So the bonds are polar. So hydrogen is a positive charge like a proton. They call protic solvent. So protic solvent can stabilize anions and make SN2 reaction less reactive, okay, because the nucleophile is stabilized. What about the solvent that has no these bonds? Okay, if the molecule's solvent has no OH, NH, SH, okay, they cannot generate protons, and therefore this solvent is called aprotic solvent. So one example you already show is methane, so hydrogen, all right, and these bonds are non-polar, so hydrogen is not positive charge, and therefore it's aprotic solvent. And this molecule is non-polar, so it's called non-polar aprotic solvent. Now here we also show some solvent that is polar aprotic solvent. For example, dimethyl sulfoxide. In this molecule, you have a carbon-hydrogen bond. Now, carbon-hydrogen bond is non-polar, so you don't have a proton. It's an aprotic solvent. But you do have a polar bond. SO bond is polar, and therefore this molecule is called a polar aprotic solvent. Similarly, dimethyl DMF, okay, dimethyl formate. So this one is a polar bond. SCO is a polar bond, but the molecule is non-polar, is aprotic, because the hydrogens are all bonded to carbon. Okay, so it's aprotic, all right, and also a polar molecule. So here HMPA, okay, polar aprotic solvent. Acetone, very common solvent, polar aprotic solvent. Acetonitrile, all right, again, hydrogen is bonded to carbon, so it's an aprotic solvent, but this bond is polar, all right. So what can polar aprotic solvent do? All right, so in protic solvent, all right, so like water, the positive charge hydrogen stabilize negative charge fluorine, so make anions less reactive. So SN2 becomes less reactive. But what about the polar aprotic solvent? Okay, in polar aprotic solvent, the bond is polar, the oxygen is negative, so it actually can stabilize cations such as sodium. Sodium is attracted to the negative charge of the oxygen, make sodium more stable. So if we add the sodium chloride in the solution, the counter ion sodium is attracted to the polar A product solvent, becomes stabilized. But the chloride is not. Okay, chloride is like a naked chloride. All right. So usually chloride is connected to sodium, so counter ion. But now counter ion is taken away. So this makes chloride ion even more unstable, very reactive. So more reactive, all right, than non-polar A product solvent. So if you add polar A product solvent, it takes sodium away, make chloride more reactive in SN2 reaction. So polar A product solvent is the most favorable for SN2 reaction. Okay, product solvent is not good, disfavor SN2 reaction. The solvation effect on SN2 reaction can also be explained by looking at the energy profile. For SN2 reaction, the reactants go through a transition state, forms the product. The energy barrier determines the reaction rate. In product solvent, the protons stabilize the anions. Anions are the nucleophiles. When the nucleophiles are stabilized, the reactant's energy goes down. And therefore, this increases the activation energy because the transition state is the same. And so when the reactants are more stable, the energy barrier increase. That slows down the SN2 reaction. So product solvent slow down SN2 reaction. On the other hand, on polar A product solvent, all right, so for example, acetone. So because this oxygen is negative charge, which can stabilize the counter ion sodium, so that make chloride, the nucleophile, becomes even more unstable. In other words, it becomes higher energy. So the reactants now becomes here, and the transition state is still the same. So that will reduce the activation energy and make the reaction go faster. So polar A product solvent, okay, destabilize the reactants and favors SN2 reaction. Here is a nucleophilic substitution reaction using primary alkyl halide, strong nucleophile. So the reaction must be SN2 reaction. Okay, now when we use product solvent, the relative reactivity 1 and 7. But if we switch to polar A product solvent, okay, the reactivity increases thousands of times. Polar A product solvents favors SN2 reaction. Okay, product solvents disfavors SN2 reaction. In the last slide, we use energy profile to show the solvent effect on SN2 reaction. So SN2 reaction has one step, and when you use product solvent, the product solvent stabilizes anion, which is a reactants. So the reaction goes down. Transition state doesn't change. This increases activation energy, and that will slow down SN2 reaction. Okay, energy profile can also be used to explain SN1 reaction. Okay, in product solvent, such as water, the negative charged oxygen can stabilize positive charged carbon cation, which is the intermediate. So in SN1 reaction, we have two steps. Okay, step 1, transition state, and forms the carbon cation, and then step 2, transition state. Now, if the carbon cation is stabilized by the product solvent, such as water, then this will reduce the activation energy. Okay, reduce the energy barrier, make reaction go faster. So product solvent destabilize, okay, defavors the SN2 reaction by stabilizing the reactants. Product solvent favors SN1 reaction by stabilizing the transition state, the intermediate, and the associated transition state, lowers the activation energy, make reaction go faster. Here shows a nucleophilic substitution reaction using tertiary alkyl halides with a very weak nucleophile. It's a solvent, okay, neutral solvent, so weak nucleophile. The reaction is obviously SN1 reaction. So when we use strong product solvent as water, the relative reaction rate is very high. If we add more ethanol, which is a weaker product solvent, then the relative reactivity becomes slow. So product solvent stabilize the carbon cation, because the first step is leaving group forms a carbon cation, and when solvent stabilizes the carbon cation, the activation energy decrease, reaction go faster for SN1 reaction. Let's summarize SN2 reaction. In a SN2 reaction, a nucleophile directly attacks carbon on the back of the halide, all right, through a transition state, forms the product. Okay, the reaction is a single-step reaction, and the product is a complete inversion of configuration compared to the reactants. SN2 reaction, both reactants, the nucleophile, the alkyl halide, are both important, and it's a second-order reaction, and that's why it's called SN2 reaction. In an SN2 reaction, a nucleophile attacks the carbon in an alkyl halide, so the substrate stirrup effect is important. The smaller, the better. So the best substrate is metal, and then primary substrate, all right, followed by secondary. Tertiary substrate do not react by SN2 reaction, okay? And also because nucleophile needs to attack alkyl halide directly, so you need a strong nucleophile. That includes negative charged basic nucleophile with high polarizability, okay? This means it needs a large size, okay, heavier. So iodide, bromide, sulfide, okay, those are good polarized nucleophiles. And strong base, such as hydroxide, methoxide, are strong base, also strong nucleophiles. Neutral solvents, such as water, carboxylic acid, these are bad nucleophiles. They are not good for SN2 reaction. Leaving group is also important for SN2 reaction, all right? So usually a stable ion, okay, corresponding to good leaving group, and this includes tosylate, iodide, bromide. They are very good leaving group. Don't forget about water. Water is also a good leaving group. But hydroxide, amide, fluoride are strong base. They are not stable, so they are bad leaving group. For solvent, we need a polar aprotic solvent, such as acetone. This solvent stabilize cations and therefore make anions, which is nucleophiles, okay, very reactive. All right, so favors SN2 reaction. On the other hand, product solvents such as water, they can stabilize anions, so they stabilize the nucleophiles and make them less reactive. So this defavors SN2 reaction. Summary of SN1 reaction. SN1 undergo two steps. The first step is carbon halide bond break, forms a carbon cation. And the carbon cation is a planar structure with an empty p orbital. And the second step is a nucleophile attack carbon cation in both faces and that gives you a racemic mixture. Now in the first step, okay, this is a slow step. This forms carbon cation. So a slow step, all right, that determines the overall reaction rate. Now in this step, the reactants only occur halide, all right. The nucleophile does not participate in the first step, so the overall reaction rate is only determined by the substrate. So this reaction is a first order reaction, because the reaction rate is only determined by alkyl halide, and that's why it's called the SN1 reaction. In SN1 reaction, the first step is the carbon halide break forms a carbon cation. So the stability of carbon cation is very important. The more stable the carbon cation, the faster the reaction goes. And that requires tertiary, allylic, and benzylic halide. Okay, this forms stable carbon cation. Now leaving group is also important, just like SN2 reaction. So tosylate, iodide, and bromide, water, those are all good leaving group. And the nucleophile, because it only participates in the second step, but the first step is the rate determining step. So nucleophiles are not very important usually in SN1 reaction. So SN1 reaction in most cases will take place in weak nucleophiles such as water, carboxylic acid. Solvent, best solvent is protic solvent. So protic solvent, because they can stabilize the carbon cation, and the carbon cation is the intermediate. When the carbon cation is stabilized, the first transition state also stabilized. That lowers the activation energy and increase the reaction rate for SN1 reaction. Again, primary alkyl halide almost always undergo SN2 reaction. Tertiary, almost always SN1 reaction. Secondary, they can undergo both mechanisms, depends on the condition. If you have a weak nucleophile, then the carbon halogen bond break forms carbon cation, and that's SN1 mechanism. But if there exists a strong nucleophile, then the nucleophile will attack directly, and that undergo SN2 reaction. Now, of course, there are eliminations may compete, so we're going to see in the next section. In addition to the alkyl halides or the substrate, we may also look at the nucleophiles and the solvent when we want to predict the reaction mechanism. And so if the nucleophile is powerful and negative charged, and usually it's SN2 reaction. If it's a weak nucleophile, such as water, alcohol, then probably SN1 reaction. For the solvent, polar aprotic solvent, probably SN2 reaction. Protic solvent, probably SN1 reaction. Practice. Predict whether the following reactions undergo SN1 or SN2 reactions. Okay, let's start with number 1. All right, so we first identify the substrate. Is this primary, secondary, or tertiary? Since it's a primary, okay, primary's alkyl halide favors SN2 reaction. So probably it's SN2 reaction. And let's look at the nucleophile. The nucleophile is sodium ion, counter ion, and OCH3 negative charge. So this is similar to hydroxide. It's a very strong base. So a strong base favors SN2 reaction. So both substrate and the nucleophile favor SN2 reaction. And the solvent is a aprotic, polar aprotic solvent. Again, it favors SN2 reaction. And this leads to the conclusion it's a SN2 reaction. Now let's look at the second one. Okay, substrate, is it primary, secondary, or tertiary? Well, this carbon connects to 3 carbon, so it is a tertiary. So it has CH3 CH3, CH3, and that's why you CH3 with 3, and there's a chlorine. All right, so tertiary substrate favors SN1 reaction, so probably it's SN1 reaction, and this is a neutral molecule like water, ethanol. It's like water, so it's a very weak nucleophile and product solvent. So all of this tells us that this is a SN1 reaction. Okay, let's look at the number C. All right, OTS, that's tosylate, very good nuclear, the leaving group. So good leaving group, but it's a secondary. So this carbon is a secondary, and a secondary substrate may undergo both, need either SN1, SN2. So this doesn't tell us whether it's SN1, SN2 reaction. So let's look at nucleophile. So sodium is a counter ion, N3 negative. Okay, if you remember in the table, this is a large negative charged ion. It's a good nucleophile. So good nucleophile favors SN2 reaction. So this favors SN2, and the solvent is polar aprotic solvent, again favors SN2 reaction. So the conclusion is it's an SN2 reaction. More practice. Which mechanism, SN1 or SN2, are most likely to occur in the following reactions? So again, we need to identify the substrate. Is this substrate primary, secondary, or tertiary? So we look at the carbon connect to the halogen, and this carbon has 3 carbons, so it's a tertiary. And the tertiary is almost always SN1 reaction. So here already tells it's probably SN1. And what about the nucleophile? It's a neutral molecule, so it's a weak nucleophile, so that favors SN1. And the solvent, this is also used as a solvent, and the solvent is a protic. Protic solvent favors SN1 reaction. So all these tells us it's a SN1 reaction. Okay, now SN1 reaction, the leaving group forms carbon cation, which is a planar structure, and then the nucleophile attack on both faces that give you a racemic mixture. So we predict it's a SN1 reaction, and the product is a racemic mixture of ethers. Okay, so that's the question number 1. Question number 2. Identify the substrate. Is this secondary, primary, or tertiary? Okay, looking at this carbon, all right, it attached to 2 carbons. So it's a secondary carbon, or secondary alkyl halide. So secondary alkyl halide doesn't tell us if it's SN1 or SN2. So we need to look at the nucleophile. And nucleophile include a heavier atom, sulfur. It's a negative charge, and that gives you a good nucleophile. A good nucleophile favors SN2 reaction. So this is probably SN2. And what about the solvent? It's a polar aprotic solvent. Again, favors SN2. And therefore, the conclusion is this is an SN2 reaction. And in an SN2 reaction, the nucleophile attack directly on the back of the halide and push the leaving group leave, and that gives you a complete inversion of chirality center. So bromine on the back, sulfur in front, all right, give you the final product. More practice. Whether the following reactions are SN1, SN2 reaction. So in the first question, this is a secondary, so you cannot tell whether SN1, SN2. And this ion, anion, okay, if you look at the table we showed before, it's not a particularly good nucleophile. It's not a bad ether, so it's fair. So it's hard to tell whether it's SN2 or SN1. All right. Now let's look at solvent. Solvent is a protic. Protic solvent favors SN1 reaction, and therefore it's likely to be SN1 reaction. Okay. In second question, and this is a primary. Primary alkyl halide almost always SN2 reaction. So this tells us this SN2 reaction. And again, this is a fail, all right, the nucleophile. And the solvent is polar A product. Polar A product favors SN2 reaction. So these combined together give you SN2 reaction. Here are the homework questions you need to work on. Problems 11.1 until 11.13. If you have time, work on additional problems 40 to 48. If you have a textbook 8th edition, then that will be 26 to 34.